Well, the last thing that we're going to do with estimation is to answer the question, how big of a sample do you need to get the results that you want? And it turns out that to answer that question, we need to realize that there's always three different things that play against each other when you have estimation. Those things are the confidence level, the margin of error, and the sample size. For the confidence level, if you wanted to be really confident of your results, almost 100% confident, then either you're going to have to go out and have a big margin of error, so you include lots of stuff, or you have to have a really big sample. If you want to have a small margin of error and be really close to the actual average or percent you're trying to estimate, then either you're going to have a huge sample, or you're going to have to be wrong now and then and have a lower confidence level. And if you want to get away with a small sample, you'll have to either have a big margin of error or a lower confidence level. When any one of those changes, the others follow. They all sort of pull against each other, so changing any one of them has to affect the others. Most of the time, we want the confidence level to be as high as it can possibly be, and the margin of error to be as low as it possibly can be. Sometimes it's outside forces that tell you what those have to be, and they just say, make this happen. Well, that means the only thing you actually have control over is the sample size. If you do make a large enough sample size, you can have any level of confidence and any margin of error you want. If you wanted to have 100% confidence and be absolutely right on the money, you'd have to have a sample size that was as big as a census. Getting really big samples can be both difficult and expensive, though, and so our goal is to figure out how big of a sample do we need. And basically to do that, it's going to boil down to working with two different formulas. The first of them is a formula we use when we want to estimate averages. And the formula looks complicated, but it's really not all that hard, and the information that you need to know is always given to you. It says that if I want to find the number I need, the n, what I have to do is take ZC, we'll find what that is in a minute, times S, which is the standard deviation, divided by E, the margin of error, and I square that. So ZC times S over E squared. Again, S is the standard deviation, and that's always given to you. E is the margin of error. If you're looking at a problem, typically the dead giveaway for that is the word within. It'll say we need to estimate this within a certain amount. The other variable that comes up in that problem is ZC. And for this, you need to go back and find the Z table that we were using in the last chapter. If you look on the side of the table that I called the big table, down at the bottom, there's a little inset that gives you these ZC values that go for different levels of confidence. Earlier I showed you the formula that was built into your calculator to find the margin of error. All this is just that exact same formula, but it's solved for n instead of e. Now this is not built into your calculator, so it is something where you'll have to use the formula to come up with it. Here's what a problem typically might look like. It says a battery manufacturer wants to know the average time their AAA batteries will last when used in calculators. They test 16 batteries in conditions similar to what calculators use, and they find that they last an average of 13.7 hours with a standard deviation of 1.9 hours. Now you might want to jot down those numbers before we go on. Again, 16 batteries, an average of 13.7 hours, and a standard deviation of 1.9. Question is, how many batteries will they have to test to estimate the actual average within 0.5 hours with 99% confidence? Again, you see the within there, that's going to be our margin of error, and they give us 99% confidence. The first thing you're going to do with this problem is go to your table. And again, if you look on the left side, down at the bottom of the big side of the table, it says confidence interval critical values ZC. And if you look up 99%, 0.99, you're going to find that the z-score that goes with that is 2.58. So that's the number we're going to use for ZC. My formula says I take ZC times S divided by E squared. They gave me everything else, and that's why we've got 2.58 times the standard deviation, which was 1.9, divided by the margin of error, 0.5, and I take that and square it, and you can see we get an answer of something like 96.118416. Something that's really important on sample size problems is you always round your answer up. You don't round the way you'd normally round. In most places in math, if you got an answer of 96.1, you would round down to 96, but here we always round up, and that's why the answer is going to be 97. The idea is that 96 wouldn't be quite enough to get the results that we want, but if you go up to 97, that'll be more than enough. So always round up. There's another formula that we'll use if we're trying to estimate percents or proportions, what we call binomial estimates. So the basic formula looks like this. And on the previous screen it said if you have an estimate of P ahead of time. P is the percent that have the kind of characteristic you want. You might remember when we were looking at the elections, I said that they always sample states ahead of time to try to get an idea of what percent are going to vote for each candidate. P would be like the probability that somebody's going to vote for a certain candidate. Your formula says P hat times Q hat, and then in parentheses we have ZC over E quantity squared. Looking at that, you probably know ZC is the same thing that we just talked about, that z-score that goes with a certain level of confidence. E is still a margin of error. And basically what P and Q are, and we'll say this officially on the next screen, is the probability of yes and the probability of no. So yeah, P hat is just the percent that have a certain characteristic, and you always write that as a decimal. So like if it was 40%, you'd put 0.4. Q hat is the percent that don't have that characteristic. If P was 40%, Q would be 60, and so you'd put 0.6. E is the margin of error. It'll always be a percent in these problems, and again, you always write it as a decimal. And ZC, again, you're going to look up in your table to find that. I said before, we use that formula if you have an idea of what P is ahead of time. And an obvious question is, well, what if you don't? And what you do if you don't is you assume it's the worst possible situation. You assume it's a 50-50 tie. It's like Florida was in that 2000 election, where you couldn't tell ahead of time what was going to happen. And what you do is you put in 0.5, 50%, for both P hat and Q hat. And so it would actually look like this, 0.5 times 0.5, and then we still have in parentheses ZC over E squared. So a typical problem. It says in the first games of the season, the players on a basketball team made 8 of 11 free throws they attempted. A sports analyst wants to predict the team's free throw percentage for the whole season. So the part that matters here is 8 out of 11. And the question is, how many attempts will have to be analyzed to estimate the season free throw percentage within 10% either way with 90% confidence? And just like when we were doing the average problems, the first thing I'm going to do is go to that table, look up 90%, And you'll notice we have 1.645 as the z-score that goes with 90%. For the p-hat, again, the important part is it told us that they got 8 out of 11 free throws. If you just divide 8 divided by 11, you get 0.72 repeating, which we could call about 0.73. So if they make 73% of their free throws, that must mean they miss 27% of them, and the q-hat would be about 0.27. Now, depending on whether you round or whether you leave the repeating decimal, you might get a slightly different answer later on in the problem, but it'll be pretty darn close. When we plug into the formula, again, it's p-hat times q-hat, zc over e squared. And so our p-hat was 0.73, our q-hat was 0.27. We looked up in the table and found out that zc was 1.645. The margin of error, again, the dead giveaway for that is within, was 10%, so 0.1. Put all of that in. You want to make sure you do have parentheses around that last part because that whole parentheses is squared. And I get about 53.3, which again, I always round up to 54. Here's another problem that you can take a look at the numbers and see if you can work out the formula with. Mr. X and Mrs. Y are running for governor. Preliminary poll shows that 57% of the voters favor Mr. X. How large of a sample should the Associated Press take to estimate the winner within 5% either way and with 95% confidence? Give you a few minutes to make sure you got those numbers right and work things out. Here you can see everything worked out with 0.57 times 0.43, 1.96 divided by 0.05, quantity squared. Again, you round up, so our answer is going to be 377 people. Another example here, the Des Moines Register is trying to estimate the percentage of Iowans who support Governor Reynolds. They don't have a previous estimate of what that rating should be. Again, the idea here is since I don't have a previous estimate, we're just going to use 50-50 for the P and Q. How many people should they sample to be within 4% of the actual approval rating with 95% confidence? Once again, the z-score is going to be 1.96. This time we have 0.5 times 0.5, and then 1.96 divided by 0.04 squared. And we have a number that rounds up to 601. Almost always you get a larger answer when you don't know ahead of time than when you do. And you notice this answer was bigger than the previous problem. It's also bigger because we have a smaller margin of error. The last example, and then you can try some problems on your own, it says you have no clue what percent of Americans shop at Walmart. My bet is quite a lot, but if you have no clue, we'll go from there. How large of a sample should you select to estimate this percentage within 3% either way with 90% confidence? Again, we'll give you a minute to type in those numbers and see what you got. This time the z-score we'll use will be 1.645. You can see the whole formula worked out there. You end up getting something like 751.6736111. Like before, we always round up, and our final answer is 752. So hopefully everything with estimation and finding sample sizes makes sense for you. You'll be doing some worksheets and of course eventually quizzes over this. Best wishes to everybody.